So it makes carbon so special. Carbon can form multiple bonds with itself and with other atoms. So single bonds, double bonds, triple bonds. Can be bonded to other carbons, or it could be bonded to oxygens, nitrogens, hydrogens, any of the halogens, all sorts of different elements that it can be bonded to and still be an organic molecule. One thing that makes carbon special is that the carbon-carbon bond is pretty strong in relation to other bonds. So it is thermally stable. So when we add energy to it, as long as we don't get too high in the energy, it's going to stay that carbon-carbon bond. It's not going to start breaking early on. The carbon-hydrogen bond is also strong and stable. Stable is especially good for us. We wouldn't want to be made out of things that are going to be really reactive with other things, because then we wouldn't be what we are. So thank goodness we're mostly organic molecules, because they're pretty stable. Carbon is special because it can form both chains and rings. And carbon cannot expand its octet to include more bonds. We know that as we go down the periodic table, we add energy levels. The more energy levels we have, the bigger the atom gets, because there's more electron shielding between the layers, and it just keeps getting bigger and bigger. With carbon, it's only in the second energy level that we have its highest energy level. So there's not a whole lot of shielding. There's 2 electrons on the inside that are blocking the nucleus's pull. So it's not like there's getting really big and it can't hold on to those electrons. So there's really only 4 bonds that it can form. It's not going to form 5 or 6 or 7 or 8. It's always going to form 4 bonds. We talked about that yesterday, which makes it really easy for us to make predictions about what types of things we're going to have, what molecules we're going to have, how many hydrogens there are going to be. We've talked about a lot of trends this semester. I just referred to one of them again with the electron shielding and the reactivity. So we've talked about ionization energy, we've talked about electronegativity, atomic radius. Those are all trends with elements. We also have trends with organic molecules. First of all, we know that carbons that form double or triple bonds are more reactive than single bonds. Triple is the most reactive of the bonds, followed by double, and then the least reactive are single bonds. We also know that when we add functional groups, this is why I asked you to take out that other packet that has the alcohols and the aldehydes, the carboxylic acid, and the amines and the amides. All of those are functional groups. They're things that are not just carbon and hydrogen. Okay, those functional groups, the more we add on, the more reactive it becomes. And these both are helpful in helping us, these are both great in helping us determine what types of reactions can occur. If I have a synthesis reaction where I break a double bond, put on 2 new molecules, 2 new atoms, 1 on each of the carbons, I can predict that. That's going to happen, and that's going to be the location that I have the reaction, not on any of the other carbon-carbon single bonds, because those aren't as reactive. So I can predict what types of products I would form. And that's how a lot of the medicines have been made over the years. If they know their starting molecule, they can add to it, make it bigger. They can start to polymerize it maybe. Maybe they want to add a hydroxyl group, an OH. So they'll say, oh, this one has a double bond. I can add an OH to this one. So they have those types of things that you guys are going to get pros at just because we know these trends. Another thing that we talk about a lot in organic chemistry is a homologous series. And that is when we have an organic molecule and we're comparing it to other molecules, and all of the members of those molecules have the same general formula. Like maybe my general formula is, CnH2n plus 2. We're You're going to see this a little later on today. This is an alkane. All alkanes, so singly bonded molecules, are going to have this formula, CnH2n plus 2, where n is however many of the carbons I have. So I have 2 times the number of carbons plus 2 of hydrogens in each one. And each time I add another H2, I'm increasing the reaction. So the neighboring members of the series differ by a CH2, and they show similar physical properties and gradation in their chemical properties. So they're going to change their chemical properties slightly in a predictable way. So that's a big word that's good to know. Homologous series. It's a good definition word to know. Talked a little bit about the trends. Those are going to be good to memorize. And next we have another important part. That important part being naming. We need to know how to name molecules, because we can get really, really long, crazy molecules that we're dealing with sometimes. So the IUPAC, the International Union of Physical and Applied Chemistry, the same people that come up with the new element names, they've come up with the system that we use to name all of our organic molecules. So the first thing that they say to do is to find and name the longest continuous carbon chain. I'm going to draw 3 molecules on here. Do these have the same number or different number in their longest continuous chain? It's the same. So even though I shaped it kind of different, it's the same thing. They all go in a row. They're both starting with a CH3 on either end and have CH2s on the inside. Just because I got a little fancy with the way I drew it, doesn't make it any different. And what I often see on tests is a question about different structural isomers, which we're going to get into in our next notes. But it asks, well, how many structural isomers does it have? These are the same structural isomer because they have 4 in a row. Okay, so even though I got a little fancy with it, still just 4 in a row. So once I find my longest continuous chain, here I have 4. So we'll keep that in mind because we're going to figure out what 4 is in a little bit. Then I'm going to identify and name any groups that are attached to that chain. In that one, I didn't have any functional groups attached to it. It was a nice, easy one. There were no special groups attached. What you then do is number the chain consecutively, starting at the end nearest whatever our functional group is. And from there, I'm going to assemble my name, listing the groups in alphabetical order. So if I have this molecule, do I have a functional group on it?
Yes.
Yes, I do. It's a hydroxyl group. If you look at your packet that I asked you to have out on the second page, where it's saying the ones to memorize, when I see an OH, what should I be thinking? Alcohol, yep. So I have an alcohol group. And I want to start counting. Well, first I need to know how many I have. I have 1, 2, 3, 4, 5, 6 carbons total. I'm in a little out of order here. So first thing, I have 6 carbons. My second thing, I know that I have an alcohol. Now I need to count from the carbon that's nearest to the carbon that this functional group is on. So I either start with the one down here or the one over here. Which one should I start with? Right or left? Right, absolutely. So 1, 2, 3, 4, 5, 6. My hydroxyl group, my alcohol functional group, is on the second carbon. That's going to become important in naming. We'll see that in just a moment. So, wherever you can find some space. Yeah.
Why does it matter which side you count from?
Just because it's part of the rules. They said let's start counting from the one that's closest to our functional group, so that's the way we do it. That way we can be consistent across the board.
Well, isn't it also because, like, if the OH was on the 5 carbon,
Mhm.
it'd be the same molecule?
It would be, but we'd start counting from the other side. Yep, so it's, yep. Yep, exactly. Yeah.
This isn't directly related to this, but
That's
you know
fine.
how for, like, we have tetrahedral and, like,
Yeah.
triple pyramid? Is
Yep.
there something similar we do for organic chemistry to describe the structure?
Not really. Not really. Because it gets a little too extensive the further on we go. Because we're adding so many different things to it. You'll see, though, that we'll build molecules of these. We just won't do it this semester. And we'll see like where the hydrogens are going to necessarily go, that sort of thing. It follows the same rules. There's just a lot more interacting with it. Okay. We'll come back to this picture in a second. First, though, we need to know some of the different names of things. So prefixes for carbon chains. If I have 1 carbon, it's meth. If it's 2, it's eth. 3 is prop. 4 is bute. 5 is pent. 6 is hex. And if I have a benzene ring, which we'll talk more about later, it's benz. These will be really good ones to memorize. So the one that I drew before on the last 2 slides ago, that had 4 in its continuous chain. How would we start writing that one out? Yep, bute. Okay, let's go back again. So suffixes, if I have no functional groups, like in my first picture that I drew, I can finish off any of my things based on what I have there. If I have only single bonds, then I'd have an A and E at the end of my word. If I had a double bond, I would say what carbon the double bond is on and then end it with "ene." If I had a triple bond, I would say which one it is and "ine" at the end. If I had 2 double bonds, I'd say which carbons they were on, and then I would say diene, because there's 2 of them. So an example of that one. Okay, I have 2 double bonds on this one. I'd start on this side for my number. Well, first of all, how many carbons do I have? 6. So I'm starting out with hex. 1, 2, 3, 4, 5, 6. Hex dash. My carbons that they're on are the first and the third. Let's just start out with where it starts. Oops. First and third. And I have 2, so di-ene. So I have 6 carbons in a row. And on the first and third carbons, I have 2 double bonds. It's another language. Gotta love a new language. Not only do we have jargon now, we have a whole brand new language. So let's go back. So we know this is bute. Are there any functional groups? No. Are there any double or triple bonds? No. So what's my suffix? Ane. Yep. So your butane here. Yeah. Like our lighters. Yay. Okay, my other one. Where did that picture go? Okay. This one's a little different because my alcohol, my hydroxyl group, we're going to end it with an OL. So rather than an ENE, like I did for my double bonds, it's going to be an OL. So I have 6 of them. How do I start out this name? Hex. And normally we keep the AN for the ane on there. Hexan. And then 2, because it's on the second carbon. And then OL. So rather than doing a full hexane, I have hexan 2-ol, because I have that alcohol group on the second carbon.